Hello there, and welcome. Tonight I want to take you somewhere special, somewhere quiet and vast, where time moves differently than it does here in your room, wherever you might be listening from right now. Perhaps you're tucked into bed, maybe you're settling into a comfortable chair, or you could be lying on a couch with the lights dimmed low. Whatever space you've chosen for this journey, I want you to know that you've made the perfect choice, because tonight we're going to explore a question together, a wondering that might seem unsettling at first glance. But I promise you, as we move through it slowly, gently, it will transform into something else entirely, something that might even help you drift off into the most peaceful sleep you've had in quite some time. The question we're going to explore tonight is about our sun, that familiar golden presence that has warmed your face on countless mornings, that star that seems so permanent, so unchanging in our daily lives. But what if I told you that scientists have discovered something remarkable about our sun's future, something that sounds dramatic when you first hear it, but becomes almost poetic when you really understand it? You see, our sun will one day, billions of years from now, grow so large that it will engulf the Earth, swallow it whole, they say. But here's the thing, and this is what we're going to explore together tonight. It's not going to happen the way you might imagine. There's no sudden gulp, no dramatic consumption. Instead, it's more like a slow tide of light. A gradual embrace that takes place over timescales so vast that our minds can barely comprehend them. Before we go any further into this cosmic story, I'd love to know where you're joining me from tonight. What corner of our beautiful planet are you resting in right now? What time is it there? Is it late at night, with stars perhaps visible through your window? Or maybe it's afternoon where you are, and you're taking a moment to rest and reset. Wherever and whenever you are, if this journey feels right to you, if you find comfort in these words and this pace, I gently invite you to like this video and subscribe to join our community of dreamers and wanderers. There's something beautiful about knowing that all around the world, at different times, in different places, people are drifting off to sleep while contemplating the same vast mysteries. We're connected in that way, you and I, and everyone else who finds themselves here. Now, as we settle in together, let me tell you why this question about the sun swallowing Earth is actually one of the most peaceful mysteries in all of astronomy. It's a question that initially sounds alarming, doesn't it? The word swallow conjures images of consumption, of endings, of something being lost forever. But what if I told you that in the language of stars, swallowing is more like breathing? What if the process is so slow, so gradual, that if you could watch it happen, it would be like watching a flower bloom in extreme slow motion, each petal unfolding over millions of years. Scientists have been studying our sun for decades now, watching it pulse and breathe, measuring its rhythms, understanding its life cycle. And what they've discovered is that stars like our sun don't die dramatically. They transform, they evolve, they change from one beautiful form to another, and in that transformation, yes, they grow larger. They expand outward like a slowly inflating balloon of light. But this expansion, this growth, it's not violent. It's almost meditative in its pace. If you could sit and watch the sun age, you would need to watch for millions of years just to notice the slightest change. That's the kind of timescale we're talking about here. Think about it this way. Right now, as you're listening to my voice, the sun is what astronomers call a main sequence star. It's in the prime of its life, steadily fusing hydrogen into helium in its core, maintaining a beautiful balance between the outward pressure of that fusion and the inward pull of its own gravity. This balance, this stellar equilibrium, has been maintained for about 4.5 billion years. 4.5 billion years. Can you even imagine such a span of time? If you tried to count to 4.5 billion counting one number per second, without stopping to sleep or eat or do anything else, it would take you over 140 years, and that's just counting, not living through all those years. The sun has been shining steadily for all that time, and it will continue to shine steadily for billions of years more. We're not talking about something that will happen tomorrow, or next year, or even in the next million years. We're talking about a future so distant that the human species as we know it today will have evolved into something unrecognizable, or perhaps will have spread across the galaxy, or maybe will have transformed in ways we can't even imagine. The timescales of stellar evolution are so vast that they make our human concerns seem like the briefest flicker of a candle flame in an endless night. But here's where it gets interesting. where the mystery deepens and becomes something beautiful rather than frightening. When the sun does eventually begin to change, when it starts its transformation from a main sequence star to what astronomers call a red giant, the process will be so gradual that if there were somehow still observers on Earth, they wouldn't notice the changes from one generation to the next. The sun might grow imperceptibly brighter over the course of millions of years. The average temperature on Earth might rise by a fraction of a degree over centuries. These changes would be like watching a mountain erode, like watching continents drift. They happen, but they happen at a pace that makes them almost invisible to our brief, human perspectives. And yet in that slow transformation, something remarkable happens. The sun doesn't just get bigger, it changes colour, shifting from the yellow-white we know now to a deeper, richer orange, and eventually to a deep red. Imagine that for a moment. Picture yourself standing on Earth billions of years from now, looking up at a sun that fills much more of the sky than it does today. But instead of that familiar yellow disk, you see a vast red orb, like a cosmic ember glowing in the heavens. The light would be different, softer perhaps, more diffuse. Shadows would be less sharp. The whole world would be bathed in this warm, red glow, like permanent sunset. But I'm getting ahead of myself. Let's slow down even more, because the beauty of this story is in the details, in the gradual unfolding of cosmic processes that operate on timescales that dwarf our human experience. You see, when we talk about the sun eventually swallowing Earth, we're really talking about a complex dance of physics, chemistry, and time. It's not a simple story of growth and consumption. It's a story of transformation, of matter and energy shifting from one form to another, of the endless cycle of stellar life and death that has been going on since the universe was young. Right now, in the sun's core, at temperatures of about 15 million degrees Celsius, hydrogen nuclei are fusing together to form helium. This process releases enormous amounts of energy that eventually makes its way to the sun's surface and then streams out into space as the light and heat that sustain life on Earth. But this process can't go on forever. The sun only has a finite amount of hydrogen fuel, and as it uses up that fuel, things begin to change. The helium that's produced by fusion is heavier than hydrogen, so it sinks to the center of the core, gradually building up like ash in a fireplace. For billions of years, this helium ash just accumulates, not doing much of anything because the temperature isn't high enough to fuse helium into heavier elements. But eventually, and we're talking about 5 billion years from now, give or take a few 100 million years, the hydrogen in the core will be mostly used up. When that happens, the balance that has kept the sun stable for so long will begin to shift. Without the outward pressure from hydrogen fusion to balance gravity's inward pull, the core will begin to contract, to squeeze in on itself. Now, you might think that would make the sun smaller, but actually the opposite happens, and this is one of those beautiful paradoxes of stellar physics. As the core contracts and heats up, the layers just outside the core, where there's still plenty of hydrogen, will get hot enough to start fusing. This shell of hydrogen fusion around the dead helium core will actually produce more energy than the core fusion does now. And all that extra energy has to go somewhere. It pushes the sun's outer layers outward, causing the sun to expand, to swell up like a balloon being slowly inflated. This is the beginning of the red giant phase, and it's a fascinating process when you really think about it. The sun becomes a giant not because it's gaining mass, but because it's restructuring itself, redistributing its matter over a much larger volume. In fact, as the sun expands, it will actually be losing mass, as the stellar wind, that stream of particles constantly flowing away from the sun, becomes stronger. It's like the sun is exhaling, breathing out part of itself into space, becoming larger but less dense, more ethereal. The numbers involved in this transformation are staggering. Our sun, which currently has a radius of about 696,000 kilometers, will expand to perhaps 200 times its current size. That means its outer layers could extend past the current orbit of Venus, possibly even reaching Earth's orbit. But here's where the "not how you think" part of our title comes in. By the time the sun reaches this enormous size, Earth's orbit will likely have changed. You see, as the sun loses mass through that stellar wind I mentioned, its gravitational grip on the planets weakens, and as that grip weakens, the planets drift outward, their orbits expanding like ripples on a pond. Scientists have calculated that by the time the Sun reaches its maximum size as a red giant, Earth's orbit could be significantly larger than it is now. Some models suggest Earth might just barely escape being engulfed, skating along just outside the Sun's expanded surface. Other models, taking into account tidal forces and the drag of the Sun's outer atmosphere, suggest Earth will spiral inward and eventually be absorbed. The uncertainty in these predictions isn't a failure of science, it's a reflection of the incredible complexity of the processes involved. But let's think about what swallowed really means in this context. We're not talking about the Sun opening some cosmic mouth and gulping Earth down like a marble. Instead, if Earth does end up inside the Sun's outer layers, it would be more like slowly sinking into an incredibly thin, incredibly hot fog. The Sun's outer layers during the red giant phase will be so diffuse, so spread out, that they'll be less dense than what we would consider a good vacuum here on Earth. It would be like being inside a glowing cloud, a luminous mist that gradually thickens as you sink deeper. And here's something else to consider, something that transforms this whole scenario from apocalyptic to almost poetic. By the time any of this happens, Earth will have been uninhabitable for billions of years already. Long before the Sun becomes a red giant, perhaps in just a billion years or so, the gradually increasing solar luminosity will have triggered a runaway greenhouse effect. The oceans will have evaporated, the atmosphere will have been stripped away, and Earth will be a barren, lifeless rock. So when we talk about the Sun eventually swallowing Earth, we're not talking about the destruction of a living world, we're talking about the recycling of a long-dead planet, its atoms returning to the star that gave them light for so long. There's something deeply peaceful about that image, isn't it? The Earth, after billions of years of orbiting the Sun, finally returning home, its matter mixing with the stellar material, becoming part of the star itself. Those atoms, the carbon and oxygen and iron and all the other elements that make up our planet, they'll be scattered into space when the Sun eventually sheds its outer layers and becomes a white dwarf. They'll drift through the cosmos, perhaps eventually becoming part of new stars, new planets, new possibilities for life. It's not an ending so much as a transformation, a continuation of the endless cycle of matter and energy that has been going on since the universe began. As you lie there listening to this story, feeling perhaps a bit drowsy, a bit dreamy, I want you to consider the profound peace in these vast timescales. Your life, my life, the lives of everyone we know and love, they're all taking place in what amounts to a single moment in the life of our star. We exist in the Sun's peaceful middle age, in a time of perfect stability, where conditions are just right for life to flourish. We're like mayflies dancing in a summer afternoon, brief and beautiful, while the Sun continues its slow, steady burn overhead. And isn't there something comforting about that? Knowing that the processes that will eventually transform our Sun and our planet operate on timescales so vast that they might as well be eternal from our perspective. It means that all our worries, all our anxieties about the future, they're playing out against a backdrop of cosmic stability. The Sun will rise tomorrow, and the next day, and every day for millions upon millions of years to come. That's a certainty we can rest in, a cosmic lullaby that says, there's time, there's so much time. Let me paint you another picture, a way of understanding these timescales that might help you drift off into peaceful sleep. Imagine the entire history of the universe, from the Big Bang to now, compressed into a single year. The Big Bang happens at midnight on January 1st. The first stars form in early January. Our Sun and solar system don't form until early September. Life on Earth doesn't appear until sometime in mid-September. The entire history of complex life on Earth, everything from the first multicellular organisms to now, that all happens in the last 2 weeks of December. Dinosaurs appear on Christmas Day and go extinct on December 29th. All of human history, from the first Homo sapiens to now, takes place in the last 14 minutes before midnight on December 31st. And the Sun becoming a red giant and potentially swallowing Earth. That doesn't happen until May of the following year. We have so much time ahead of us, so much future stretching out, before our species, before our planet, before our star. And in that vast expanse of time, who knows what wonders await? Perhaps humanity will develop technologies we can't even imagine now. Perhaps we'll spread across the galaxy, carrying Earth's legacy to 1,000 different worlds. Perhaps we'll learn to move planets, to adjust orbits, to manage stars themselves. Or perhaps we'll evolve into something so different from what we are now that these concerns will seem quaint, like worrying about running out of flint for making fire. But for now, for tonight, we can rest in the knowledge that we exist in a moment of perfect balance, a time when the sun shines steadily, warming our world just enough for life to thrive. We're part of a cosmic story that stretches billions of years into the past and billions of years into the future, and right now, right at this moment, we get to be conscious witnesses to it all. We get to look up at the stars and wonder. We get to ask questions about our cosmic future. We get to tell stories about what might be. And speaking of stories, let me share with you some of the remarkable ways scientists have peered into our sun's future, how they've managed to predict with surprising accuracy what will happen billions of years from now. It's a testament to human ingenuity that we can look at other stars in various stages of their lives and see our own sun's future written in their light. We can observe red giants in distant parts of our galaxy and say, that's what our sun will look like someday. We can study white dwarfs, the remnants of stars like our sun, and know that's our star's ultimate fate. The story of how we know what we know is almost as fascinating as the cosmic story itself. It begins with observations of thousands upon thousands of stars, each one a sun in its own right, each one at a different stage of its life. By studying these stars, measuring their brightness, their colour, their size, their chemical composition, astronomers have pieced together the life cycle of stars like our sun. It's like walking through a forest and seeing trees of all different ages, from seedlings to ancient giants to fallen logs, and from that snapshot, understanding the entire life cycle of a tree. We've sent spacecraft to study the sun up close. The Solar and Heliospheric Observatory, or SOHO, has been watching the sun continuously for over 2 decades, observing its surface, its atmosphere, its constant activity. The Solar Dynamics Observatory captures images of the sun in multiple wavelengths, revealing the complex magnetic fields that dance across its surface, the solar flares that erupt like cosmic fireworks, the steady pulse of our star's heartbeat. The Parker Solar Probe has actually touched the sun's atmosphere, flying through the corona, gathering data about the solar wind and the sun's magnetic field that we could never get from Earth. All of this observation, all of this data, it feeds into complex computer models that simulate the sun's evolution over billions of years. These models take into account nuclear physics, thermodynamics, gravity, magnetism, and countless other factors. They're run on supercomputers, calculating the interactions of billions of particles, the flow of energy from core to surface, the gradual changes that accumulate over cosmic time. And remarkably, when we run these models for stars of different masses and compositions, and then look for real stars that match those predictions, we find them. The models work. They accurately predict what we observe in the universe. This gives us confidence that when we model our own sun's future, we're seeing something real, something that will actually happen, even if it's billions of years away. The red giant phase isn't speculation or science fiction. It's a scientific prediction based on solid physics and countless observations. We can calculate fairly precisely when it will happen, how large the sun will grow, how its luminosity will change, what will happen to its core temperature and pressure. The uncertainty isn't in whether it will happen, but in some of the details, like exactly how Earth's orbit will evolve, exactly when certain transitions will occur. And you know what's beautiful about this? The same physical laws that govern the sun's evolution govern everything else in the universe. The fusion reactions happening in the sun's core right now follow the same rules as fusion reactions in stars on the other side of the galaxy, in other galaxies, even in the most distant galaxies we can see. The gravity that holds the sun together is the same gravity that keeps your feet on the ground, that keeps the moon orbiting Earth, that shapes the structure of galaxy clusters. We're all part of the same cosmic story, governed by the same elegant laws of physics. As you drift deeper into relaxation, perhaps feeling your breathing slow, your muscles relax, I want to share something else about the sun's distant future, something that brings the story full circle in a beautiful way. After the red giant phase, after the sun has shed its outer layers and shrunk down to a white dwarf about the size of Earth, but with a mass close to what it has now, it will slowly cool over trillions of years. Yes, trillions. The universe is only about 14 billion years old now, so we're talking about timescales that are hundreds of times longer than the current age of the universe. During this cooling phase, the white dwarf that was once our sun will be incredibly dense. A teaspoon of its matter would weigh as much as a car. It will start out incredibly hot, hotter than the sun's surface is now, but over those trillions of years it will gradually cool, its light shifting from white to yellow to orange to red, and eventually, in a future so distant it's almost meaningless to contemplate, it will fade to black, becoming a cold, dark sphere of crystallized carbon and oxygen, cosmic diamond the size of Earth. But even that's not really the end. That cold, dark remnant will continue to exist, essentially forever. It will orbit the center of the galaxy, perhaps occasionally passing close to other stars, maybe even being captured into a binary system with another stellar remnant. The atoms that make it up, forged in the Big Bang and in previous generations of stars, will continue their cosmic journey. They're essentially immortal, these atoms, and they carry with them the history of everything they've been part of. Some of those atoms were once part of Earth, some were once part of living things, some were once part of you and me, because we're all made of star stuff, as Carl Sagan so beautifully put it. The calcium in your bones, the iron in your blood, the carbon in your DNA, these atoms were forged in the cores of dying stars billions of years ago. And someday, billions of years from now, they'll be part of something else, perhaps part of new stars, new planets, new life forms we can't even imagine. This is the real story of the sun swallowing Earth. It's not a story of destruction, but of transformation. It's not a story of endings, but of cycles. It's not a story that should frighten us, but one that should fill us with awe at the incredible, intricate, beautiful universe we're part of. We exist in a cosmos where stars are born, live for billions of years, and then transform into something else, spreading their enriched matter through space to seed new generations of stars and planets. We exist in a universe where matter and energy are conserved, where nothing is ever really lost, just change from one form to another, and we exist at a particular moment in this cosmic story, a moment when conditions are just right for us to be here, to be conscious, to be able to look up at the stars and understand our place in the universe. We're the universe becoming aware of itself, if you think about it. These atoms that have been cycling through cosmic history for billions of years have temporarily arranged themselves into patterns complex enough to think, to wonder, to ask questions about their own future. That's remarkable. That's miraculous, really, in the deepest sense of the word. So as you lie there, perhaps feeling sleepy now, perhaps already drifting at the edges of dreams, remember that you're part of this vast, slow, beautiful cosmic dance. The sun that will rise tomorrow morning, or that set this evening, depending on where you are, is the same sun that has been rising and setting for billions of years, and will continue to do so for billions more. Its light, travelling 93 million miles through space, takes about 8 minutes to reach Earth. But the energy in that light was generated in the sun's core perhaps 1 million years ago, slowly working its way to the surface through countless interactions, countless absorptions and re-emissions, until finally breaking free and streaming across space to warm your face. That's the pace of stellar time, the rhythm of cosmic processes. Things happen, but they happen slowly, gently, giving life time to adapt, to evolve, to flourish. The sun's eventual transformation into a red giant is part of this same slow rhythm. It's not a catastrophe waiting to happen. It's a natural progression, as natural as a tree growing from a seed, flourishing for years, and eventually returning its matter to the soil. It's the way of stars, the way of the universe, and there's a deep peace in accepting and understanding these vast cycles. In the chapters ahead, we'll explore more deeply the actual mechanisms of stellar evolution, the fascinating physics that drives these transformations. We'll look at what scientists have learned from studying other stars that have already gone through what our sun will experience. We'll consider the various scenarios for Earth's fate, from the possibility that it might escape engulfment to the possibility that it might spiral into the sun's expanded atmosphere. We'll explore what these distant events mean for us here and now, how thinking about cosmic time can change our perspective on our daily lives. But for now, for this moment, just rest in the knowledge that you exist in a stable, peaceful moment in cosmic history. The sun is shining steadily, Earth is orbiting faithfully, and you have all the time you need to rest, to dream, to let your mind wander through these vast spaces and times. There's no hurry in the cosmos. Everything unfolds at its own pace, in its own time, following the deep patterns and laws that govern all of existence. The story of the sun and earth is ultimately a love story if you think about it. A story of a star and its planet, bound together by gravity, dancing together through space for billions of years. The sun gives Earth light and warmth, the essential energy for life. Earth gives the sun a companion, a witness to its long life. They've been together since the beginning, formed from the same cloud of gas and dust 4.6 billion years ago, and they'll be together until the end, whatever form that end might take. It's a cosmic romance played out over timescales that dwarf human comprehension, but it's beautiful in its simplicity, its faithfulness, its inevitability. Consider the possibility that when we talk about the sun eventually swallowing Earth, we're really talking about a reunion, a coming home. The matter that makes up Earth came from the same nebula that formed the sun. We've been circling our parent star for billions of years, like a child orbiting a parent, always connected but maintaining our distance. And someday, in that far distant future, we might return to the source, our atoms mixing once again with solar material, becoming part of the star that gave us life. There's poetry in that, don't you think? A cosmic cycle completing itself, a story coming full circle. The scales of time we're discussing tonight might seem overwhelming at first, these billions and trillions of years that stretch out before us. But there's something liberating about contemplating such vastness. It puts our human concerns into perspective. That deadline you're worried about, that conflict you're struggling with, that uncertainty about the future, when viewed against the backdrop of stellar evolution, these concerns become manageable, temporary, part of the brief flicker of human experience against the vast continuity of cosmic time. And yet, paradoxically, understanding these vast timescales can make our brief lives feel more precious, not less. We exist in this particular moment, this particular arrangement of atoms and energy, for such a short time compared to the life of stars. But in that short time, we get to experience consciousness, emotion, wonder. We get to love and be loved. We get to create and discover and dream. We get to look up at the night sky and understand, at least partially, our place in the grand scheme of things. That's extraordinary. That's a gift beyond measure. The sun that warms your face tomorrow will be essentially identical to the sun that warmed the faces of your ancestors thousands of years ago, and will warm the faces of your descendants thousands of years from now. It's a constant in human experience, a touchstone that connects us across time and space. Every human who has ever lived has known the same sun, felt its warmth, watched it rise and set, marked the passage of days and seasons by its movement across the sky. And every human who will ever live, for millions of years to come, will know this same sun, this same faithful star that makes life on Earth possible. When astronomers first began to understand stellar evolution, when they first realized that our sun would eventually become a red giant, there was indeed a moment of existential vertigo, a recognition that even our star, seemingly eternal and unchanging, was mortal, was evolving, would someday be something other than what it is now. But as our understanding has deepened, as we've learned more about the incredible slowness of these changes, the vast timescales involved, that initial alarm has transformed into something more like awe, more like appreciation for the incredible stability we enjoy. We live in what astronomers sometimes call the habitable epoch of the universe, a time when stars like our sun can form and burn steadily for billions of years, when rocky planets can form and maintain stable orbits, when the conditions for life as we know it can persist for enormous spans of time. This epoch won't last forever, nothing does, but it will last for trillions of years to come. We exist near the beginning of this habitable epoch, with an almost unimaginable future stretching out before us. And within our sun's life, we exist in what you might call its golden age, a period of stability and consistency that has already lasted billions of years and will continue for billions more. The sun's luminosity is increasing very gradually, about 1% every 100 million years, but this change is so slow that life on Earth has had plenty of time to adapt. In fact, Earth's climate has remained remarkably stable despite this gradual brightening, thanks to various feedback mechanisms, including the carbon cycle and the slow evolution of life itself. Think about that for a moment. Life on Earth has actually been adjusting to the sun's slowly increasing brightness for billions of years, and doing it so successfully that the planet's average temperature has remained within a range suitable for liquid water for all that time. It's a kind of cosmic dance, with life and the planet's geology responding to the sun's gradual changes, maintaining a delicate balance that has persisted for eons. This gives us hope that life, in some form, might persist far longer than we might initially think, perhaps finding ways to adapt to the sun's continued brightening for hundreds of millions or even billions of years to come. But let's return to that distant future, to the time when the sun begins its transformation into a red giant. One of the most fascinating aspects of this process is how gradual it will be. The sun won't suddenly balloon outward one day. Instead, over the course of hundreds of millions of years, it will slowly expand, slowly cool at its surface even as its core grows hotter, slowly shift its colour from yellow-white to orange to red. If you could watch this process in fast forward, it would look like the sun is breathing out, exhaling over millions of years, its surface rippling and flowing like a vast ocean of plasma. During this red giant phase, the sun will experience something called thermal pulses, periods where the rate of fusion in its shell increases, causing the star to brighten and expand, followed by periods of relative calm. These pulses might last thousands of years each, mere moments in stellar time, but each one will send waves of matter streaming away from the sun, enriching the space around it with heavier elements. It's like the sun will be seeding space with the materials for future generations of stars and planets, spreading its wealth across the cosmos. And here's something beautiful to contemplate as you drift towards sleep. Those atoms that stream away from the sun during its red giant phase, they don't just disappear. They become part of what astronomers call the interstellar medium, the thin gas and dust that fills the space between stars. This material can eventually collapse under its own gravity to form new stars, new planets, new possibilities for life. The death of one star becomes the birth of others. The universe recycles everything, wasting nothing, transforming matter and energy in an endless cosmic dance. Some of those atoms from our sun might one day be part of planets orbiting other stars. Some might become part of living beings on those planets, if life emerges there. The carbon that makes up your body right now was forged in the core of a star that died before our sun was born. And the carbon in your body might one day, billions of years from now, after the sun has gone through its red giant phase and shed its outer layers, become part of some other living being on some other world orbiting some other star. We're all temporary arrangements of ancient atoms, brief patterns in the flow of matter and energy through time. This interconnectedness, this continuity across cosmic time, it's both humbling and elevating. We're small, yes, brief, certainly, but we're also part of something immense and ongoing. We're not separate from the universe. We are the universe, arranged temporarily into this particular pattern, this particular consciousness, this particular moment of awareness. The sun's story is our story. Earth's story is our story. And their future, however it unfolds, is part of the same grand narrative that includes us right now, right here, in this moment. As we prepare to move deeper into the science of stellar evolution, into the specific mechanisms that will drive the sun's transformation, I want you to carry with you this sense of peace about these vast processes. Yes, the sun will eventually swallow Earth, or at least come very close to doing so, but this isn't a disaster waiting to happen. It's a natural progression, as natural as the changing of seasons, just played out over incomprehensibly longer timescales. It's the universe doing what the universe does, changing, evolving, transforming, creating new from old, forever and always. The atoms that make up your body have already been on incredible journeys. They've been part of stars, part of interstellar clouds, part of planets, possibly part of other living beings. They've experienced the intense heat of stellar cores and the cold of interstellar space. They've been bound together in countless different configurations, and they'll continue their journey long after you're gone, long after Earth is gone, long after the sun has become a white dwarf. You are, in a very real sense, the universe experiencing itself, a temporary eddy in the flow of cosmic matter and energy that has somehow become conscious, become aware, become capable of contemplating its own nature and future. So rest easy tonight, knowing that you're part of this vast, slow, beautiful process. The sun will rise tomorrow, as it has for billions of years. Earth will continue its faithful orbit, as it has since its formation. And you, made of star stuff, animated by the same energy that powers the stars, will continue your own journey through this cosmic story, however long or brief it might be. There's no rush, no urgency. Everything happens in its own time, at its own pace, following the deep patterns that govern all of existence. In the silence between stars, in the vast spaces that separate celestial bodies, there's a profound quiet, a cosmic calm that underlies all the activity and transformation. Even as stars are born and die, even as galaxies collide and merge, even as the universe itself expands and evolves, there's a fundamental peace to it all, a sense that everything is unfolding exactly as it should. The sun's eventual transformation, Earth's ultimate fate, these are just notes in a cosmic symphony that has been playing for 14 billion years and will continue playing for trillions more. As we move forward into exploring the deeper science, the specific details of how stars evolve and what that means for planets like Earth, remember this feeling of cosmic peace. Let it be the foundation for understanding these vast processes. Because when you really understand the timescales involved, when you truly grasp how slow and gradual these changes are, there's nothing to fear, nothing to worry about. There's only wonder, only awe at the incredible universe we're privileged to be part of, even for our brief moment in the cosmic dance. The story continues, the dance goes on, and we're here to witness it, to understand it, to be part of it. The sun that will eventually swallow Earth is the same sun that makes life possible today. The processes that will transform our star are the same processes that created the elements that make up our bodies. We're not separate from this story. We're woven into its very fabric, essential threads in the cosmic tapestry. And that, perhaps more than anything else, is the peaceful truth that can carry you off into the sweetest of dreams tonight. Now, as we transition into thinking about the vast scales of time and space that govern these stellar processes, I want you to imagine something with me. Picture yourself floating gently above Earth, looking down at our beautiful blue marble of a planet, seeing the swirls of clouds, the deep blues of oceans, the browns and greens of continents. Now, slowly, begin to pull back, to zoom out like a cosmic camera, watching Earth shrink to a point of light, watching the sun come into view, that brilliant star that has been our constant companion for so long. Keep pulling back, and you'll see the other planets come into view, Mercury hugging close to the sun, Venus shrouded in its thick atmosphere, Mars glowing red in the distance and beyond, the giant planets Jupiter and Saturn, Uranus and Neptune. Our whole solar system, everything we've ever known, it all orbits around that one star, our sun, held in place by invisible threads of gravity, dancing to a cosmic rhythm that's been playing for billions of years. But keep pulling back further, and even our sun becomes just another point of light, one star among hundreds of billions in our galaxy. And if you could keep going, pulling back until even our galaxy is just a smudge of light, you'd see that it's one of hundreds of billions of galaxies in the observable universe, each one containing hundreds of billions of stars, many of them going through the same life cycles as our sun, many of them in different stages of that cosmic journey from birth to transformation. This is the scale we're talking about when we discuss stellar evolution. These are the vast spaces and times in which these processes play out. And yet, somehow, in all that immensity, on one small planet orbiting one ordinary star in one spiral arm of one galaxy, atoms have arranged themselves into patterns complex enough to look back at the universe and understand it. That's you, that's me, that's all of us. We're the universe's way of knowing itself, of understanding its own processes, of contemplating its own future. When scientists first began to understand these scales, when they first realized just how vast the universe is and how long these stellar processes take, there was a moment of existential vertigo, a recognition of just how small and brief human life is in comparison. But that initial shock has given way to something else, something more like wonder, more like gratitude for the incredible privilege of being conscious in such a vast and beautiful cosmos. We may be small, we may be brief, but we're here, we're aware, and we get to be part of this incredible story. The sun's eventual transformation into a red giant, its possible engulfment of Earth, these events are so far in the future that they're almost abstract, almost mythological. They're real, they will happen. but they exist in a future so distant that it might as well be another universe entirely. Between now and then, there's room for millions of human generations, for the rise and fall of countless civilizations, for evolutionary changes we can't even imagine, for technological developments that might seem like magic to us today. Who knows what humanity might become in those billions of years? We might spread across the galaxy, establishing colonies on thousands of worlds. We might learn to harness the energy of stars themselves, to move planets, to create new life, to transcend our biological limitations in ways we can't even conceive of now. Or we might evolve into something entirely different, something that would look back at us the way we look back at the first single-celled organisms. The future is vast and open, full of possibilities we can barely imagine. But even if humanity doesn't survive to see the sun's transformation, even if we're just a brief chapter in Earth's long story, we've still been part of something magnificent. We've been the universe's way of understanding itself, of appreciating its own beauty, of contemplating its own mysteries. Every time you look up at the stars, every time you wonder about the cosmos, you're fulfilling a cosmic purpose. You're completing a circuit that began with the Big Bang and continues through you to the far future. The atoms in your body have been on a journey that began in the first moments after the Big Bang, when the universe was hot and dense and simple, just hydrogen and helium and radiation. Those atoms have been through the cores of stars where they were transformed into heavier elements. They've drifted through interstellar space cold and alone. They've been part of planets, possibly multiple planets over cosmic time. They've been part of rocks and water and air. And now, for this brief moment, they're part of you, arranged in such a way that they can think and feel and wonder. And someday, those atoms will continue their journey. They'll return to the earth when you die, becoming part of soil, part of other living things. Eventually, billions of years from now, they might be part of the sun's outer layers during its red giant phase. They might be blown out into space when the sun sheds those outer layers, becoming part of a planetary nebula, a beautiful shell of glowing gas expanding into space. They might eventually become part of new stars, new planets, new life forms in some distant future we can't imagine. This is the real story of stellar evolution, the real meaning of the sun eventually swallowing Earth. It's not about destruction, it's about transformation. It's not about endings, it's about continuity. It's not about loss, it's about the endless recycling of matter and energy in a universe that wastes nothing, that transforms everything, that creates endless new possibilities from the ashes of the old. As you continue to relax, to sink deeper into that peaceful state between waking and sleeping, I want you to feel yourself as part of this vast process. You're not separate from the cosmos. You're woven into it at every level. The iron in your blood was forged in a supernova. The calcium in your bones was created in the heart of a massive star. The water in your body has been cycling through Earth's oceans and atmosphere for billions of years. You're ancient in a way, made of materials that have existed since the early universe. And you're also brand new, a unique arrangement of those materials that has never existed before, and will never exist again in quite the same way. The sun that will rise tomorrow, or that set this evening, is engaged in a process of nuclear fusion that's been going on for billions of years and will continue for billions more. Every second, it converts about 600 million tons of hydrogen into helium, releasing energy that lights up our solar system, that drives the weather on Earth, that powers photosynthesis in plants, that ultimately provides all the energy for life on our planet. It's a generous star, our sun, constantly giving of itself, constantly transforming matter into energy and sending that energy out into space. And we're the beneficiaries of that generosity. Every calorie of food you've ever eaten ultimately came from the sun's energy. Every breath you take is possible because of the sun's light driving photosynthesis, creating the oxygen we breathe. Every moment of warmth you felt from sunlight is a gift from our star, a small portion of its enormous energy output that happened to fall on you. We're solar-powered beings, in the most fundamental sense, children of our star, dependent on its steady output for everything we are and everything we do. When we think about the sun eventually swallowing Earth, we should remember this relationship, this billions-year partnership between star and planet, between sun and life. It's been a good partnership, a fruitful one that has resulted in the incredible diversity of life we see on Earth today, including us. And when that partnership eventually ends, when Earth either spirals into the sun or is vaporized by its heat, it will be like a child returning to its parent, a completion of a cycle that began when both Sun and Earth formed from the same nebula 4.6 billion years ago. There's no tragedy in this, no cosmic injustice. It's simply the way of stars and planets, the natural progression of celestial bodies through time. Just as we don't mourn for a flower that blooms and then fades, we shouldn't mourn for a planet that has its time in the habitable zone and then returns to its star. It's all part of the same process, the same cycle, the same beautiful dance of matter and energy through time and space. And remember, by the time any of this happens, Earth will have had an incredible run. It will have orbited the Sun billions upon billions of times. It will have hosted life for at least 3.5 billion years, possibly longer. It will have seen the rise and fall of countless species, the evolution of consciousness, the development of beings capable of understanding their own cosmic situation. That's a magnificent legacy for any planet, a story worth celebrating rather than mourning. As we prepare to explore the specific mechanisms of stellar evolution in more detail, to understand exactly how and why the Sun will transform into a red giant, I want you to carry with you this sense of cosmic perspective, this peaceful acceptance of the vast processes that govern our universe. The Sun's transformation isn't something to fear. It's something to marvel at, to appreciate, to understand as part of the grand story of cosmic evolution. We're about to journey into the heart of stars, to understand the nuclear processes that power them, the balance of forces that keeps them stable, and what happens when that balance finally shifts. We'll explore how astronomers have pieced together this story from observations of countless stars, each one a laboratory for understanding stellar physics. We'll see how computer models can simulate billions of years of stellar evolution, compressing cosmic time into calculations we can comprehend. But as we delve into these details, remember the larger picture. Remember that we're talking about processes so slow, so gradual, that they might as well be eternal from a human perspective. Remember that we exist in a moment of perfect stability, with billions of years of similar stability ahead of us. Remember that the Sun's eventual transformation is not a disaster, but a natural progression, as natural as the changing of seasons or the cycle of life and death we see all around us. The universe is patient, it doesn't hurry. Stars take billions of years to exhaust their fuel. Galaxies take hundreds of millions of years to rotate once. The universe itself has been expanding for 14 billion years and will continue expanding for trillions more. In all this vastness, in all this slow majesty, we exist for our brief moment, conscious and aware, able to appreciate the beauty and grandeur of it all. That's our gift, our privilege, our cosmic role. So as you drift deeper into relaxation, perhaps beginning to feel that soft edge of sleep approaching, know that you're part of this vast, patient universe. There's no rush, no urgency. Everything happens in its own time, including your own journey into sleep and dreams. The Sun will be there tomorrow, continuing its steady burn, continuing its slow journey through stellar evolution. Earth will continue its orbit, faithful as always. And you'll wake to another day in this cosmic story, another opportunity to be a conscious part of the universe's long, beautiful evolution. The story of the Sun swallowing Earth is really the story of the universe itself, constantly changing, constantly transforming, but never rushing, never hurrying, always taking exactly as much time as it needs. And in that cosmic patience, that stellar slowness, there's a profound peace, a deep tranquility that we can tap into whenever we need it. Just remember, you're made of star stuff, you're powered by sunlight, and you're part of a story that stretches from the Big Bang to the far distant future. A story in which every chapter is necessary, every moment has its place, and everything transforms, but nothing is ever truly lost. Now let us continue our journey deeper into the cosmic mystery, into the very heart of our star, where the processes that will one day transform the Sun are already at work, have been at work for billions of years, and will continue their patient labour for billions more. As you settle even deeper into comfort, perhaps adjusting your position slightly, finding that perfect spot where your body can completely relax, I want to take you on a journey through scales of time so vast that they transform our entire understanding of what it means for something to happen, what it means for things to change, what it means for time itself to pass. Imagine, if you will, that we could slow down our perception of time, or rather speed it up so dramatically that we could watch the cosmos evolve like a time-lapse film. If we could do this, if we could compress millions of years into seconds, we would see the most remarkable dance unfolding above us. Stars would appear like fireflies, blinking into existence, glowing steadily for what would seem like moments, then fading, or exploding in tiny flashes of light. Galaxies would spin like pinwheels, their spiral arms winding and unwinding in graceful curves. The entire universe would pulse with activity, with creation and destruction, with transformation and renewal. But here's the beautiful paradox. From our human perspective, living our brief lives of decades, the universe appears almost perfectly still. The stars seem fixed in their positions, unchanging night after night, year after year, generation after generation. The sun rises and sets with such reliability that we've built our entire civilization around its rhythm. This contrast, this difference between cosmic time and human time, is not a bug in the system, it's a feature. It's what allows us to exist at all, to have stable conditions long enough for life to evolve, for consciousness to emerge, for beings like us to develop the ability to contemplate our own existence. Scientists have calculated that if you were to watch the sun continuously for your entire lifetime, say 80 years, you would not be able to detect any change in its size, its temperature, or its luminosity with the naked eye. The changes are happening, yes, but they're happening at a rate that's roughly 1 billion times slower than the rate at which we experience change in our daily lives. It's like trying to watch a mountain erode or a continent drift. The process is real, it's happening, but it's occurring at a pace that makes it essentially invisible to human perception. Let me give you another way to think about this. The sun fuses about 600 million tons of hydrogen into helium every single second. That sounds like a lot, and it is. It's an almost incomprehensible amount of matter being transformed into energy. But the sun contains about 2 times 10 to the 30th kilograms of matter. That's a 2 followed by 30 zeros. At the current rate of fusion, it would take the sun about 10 billion years to fuse just 10% of its total hydrogen. And it doesn't even need to fuse all its hydrogen. It only needs to fuse the hydrogen in its core, about 10% of the total, before it begins its transformation into a red giant. This is the kind of fuel efficiency that we can barely comprehend. If your car could run with this kind of efficiency, you could drive it continuously at highway speeds for billions of years on a single tank of gas. The sun is the ultimate slow-burn engine, converting its fuel into energy at a rate that's perfectly balanced to provide stable conditions for billions of years. It's not too fast, which would exhaust the fuel quickly and leave us in darkness, and it's not too slow, which wouldn't provide enough energy to warm Earth and power life. It's just right, a cosmic Goldilocks scenario that we're the beneficiaries of, and this brings us to one of the most profound realizations in all of astronomy. The universe seems to be fine-tuned for slow, gradual change, for stability over vast periods of time, for the kind of conditions that allow complexity to emerge and evolve. If the fundamental constants of nature were even slightly different, if the force of gravity were a bit stronger or weaker, if the nuclear forces that govern fusion were slightly altered, stars might burn out in millions of years instead of billions, or they might never ignite at all. The fact that stars like our sun can burn steadily for 10 billion years is a consequence of the fundamental laws of physics being exactly what they are. Now, as we contemplate these vast timescales, I want you to consider something that might seem counterintuitive at first. The very slowness of stellar evolution, the fact that it takes billions of years for a star to exhaust its fuel and transform, this isn't separate from our existence, it's the prerequisite for it. Life as we know it required billions of years to evolve from simple, single-celled organisms to the complex forms we see today, including us. If stars burned out in millions of years instead of billions, there wouldn't have been enough time for this evolution to occur. We exist because the universe operates on these vast timescales, not in spite of them. Think about the journey that life on Earth has taken. For the first billion years or so after Earth formed, there was no life at all. Just a hot, chaotic young planet, slowly cooling and stabilizing. Then, somehow, somewhere, perhaps in a warm pond or near a deep-sea volcanic vent, the first self-replicating molecules appeared. These weren't living things as we would recognize them. just chemical systems that could make copies of themselves, passing on information from one generation to the next. For perhaps another 1.5 billion years, life remained microscopic, single-celled, simple. It was only about 600 million years ago, in what scientists call the Cambrian explosion, that complex multicellular life really took off, diversifying into the myriad forms that would eventually lead to everything we see today. Dinosaurs didn't appear until about 230 million years ago. The first mammals evolved around 200 million years ago. Our own species, Homo sapiens, has existed for only about 300,000 years, a mere eye blink in cosmic time. All of this evolutionary history, all of this gradual development of complexity and consciousness, it was only possible because the sun provided a stable energy source for all those billions of years. If the sun were more variable, if it had periods of dramatically increased or decreased output, life might never have gotten past the single-cell stage, or might never have emerged at all. The stability of our star over cosmic time is what allowed the instability and change necessary for evolution to produce the incredible diversity of life we see on Earth today. And here's something even more remarkable to consider. The sun's gradual brightening over billions of years, that 1% increase in luminosity every 100 million years I mentioned earlier, has actually been a driver of evolution on Earth. As the sun has slowly gotten brighter, life and Earth's climate system have had to adjust, and these adjustments have led to innovations, to new forms of life, to increased complexity. The Great Oxidation Event, when photosynthetic bacteria filled the atmosphere with oxygen about 2.4 billion years ago, was partly a response to the need to process increasing solar energy. The evolution of complex cells with nuclei, the development of multicellular life, the colonization of land by plants and animals, all of these major transitions in the history of life were influenced by the slowly changing solar input. So when we think about the sun eventually becoming a red giant, we're not just thinking about the end of Earth as we know it. We're thinking about the culmination of a 10 billion year relationship between a star and its planets, a relationship that has already produced wonders beyond imagination and may yet produce wonders we can't even conceive of in the billions of years remaining. The transformation of the sun is not separate from the story of life on Earth. It's the final chapter of that story, or perhaps the transition to a new story we can't yet imagine. Let me take you deeper into this idea of cosmic time as a river, a slow, steady flow that carries everything along at its own pace. Rivers shape landscapes not through violent action but through patient persistence. Water flowing over rock for millions of years carves grand canyons. Similarly, the flow of cosmic time shapes stars and planets, galaxies and clusters, not through sudden changes but through the accumulation of tiny alterations over incomprehensible spans of time. The sun's core, where fusion takes place, is slowly changing its composition. With each fusion reaction, 4 hydrogen nuclei combine to form one helium nucleus, and that helium is slightly heavier than hydrogen, so it sinks toward the center of the core. Over billions of years, a helium-rich center has been growing in the heart of our star, like a pearl forming grain by grain in an oyster. This helium core doesn't participate in fusion yet. The temperature isn't high enough for helium fusion, so it just sits there, gradually growing larger, gradually changing the dynamics of the sun's interior. This process is so slow that if you could somehow take a snapshot of the sun's interior today and compare it to a snapshot from 1,000 years ago, you wouldn't be able to detect any difference. You'd need snapshots separated by millions of years to see the gradual accumulation of helium, the slow depletion of hydrogen in the core, the subtle changes in temperature and pressure that are gradually inexorably leading toward the sun's eventual transformation. And yet, despite this incredible slowness, the process is accelerating, though acceleration in stellar terms still means changes over millions of years. As the helium core grows, the remaining hydrogen in the core is compressed into a smaller volume, which makes it slightly hotter, which makes fusion proceed slightly faster, which makes the sun slightly more luminous. This is why the sun is slowly brightening over time. It's a feedback loop, but one that operates over such vast timescales that it might as well be standing still from our perspective. Scientists have modelled this process in incredible detail, using sophisticated computer simulations that track the behaviour of matter and energy throughout the sun's interior. These models divide the sun into thousands of shells, like the layers of an onion, and calculate how energy flows from the core to the surface, how matter circulates in convection currents, how the composition changes over time. The models must account for quantum mechanics, which governs the fusion reactions, thermodynamics, which describes how energy flows, hydrodynamics, which explains how the plasma moves, and general relativity, which affects how gravity operates in the Sun's intense field. When these models are run forward in time, simulating millions and billions of years of stellar evolution, they paint a detailed picture of our Sun's future. About 1.2 billion years from now, the Sun will be about 10% more luminous than it is today. That might not sound like much, but it's enough to trigger dramatic changes on Earth. The increased solar heating will accelerate the weathering of silicate rocks, which removes carbon dioxide from the atmosphere. This might sound good at first, like a natural counterbalance to global warming, but eventually CO2 levels will drop so low that plants will no longer be able to photosynthesize. Without plants, the food chain collapses, oxygen production stops, and complex life as we know it becomes impossible. But let's not dwell on that particular milestone, because remember, we're talking about 1.2 billion years from now. To put that in perspective, 1.2 billion years ago, the most complex life on Earth was single-celled organisms. The entire evolution of complex life, from the first multicellular organisms to humans, has taken less time than the remaining habitable period Earth has ahead of it. Who knows what life might become in that time? What new forms might evolve? What solutions might be found? Perhaps life will move underground or into the oceans, finding refuge from the increasing heat. Perhaps new forms of photosynthesis will evolve that can work with lower CO2 concentrations. Perhaps, and this is not as far-fetched as it might sound, intelligent beings, whether our descendants or something else entirely, will find ways to adjust Earth's orbit, moving it gradually outward to compensate for the Sun's increasing brightness. The point is, we're talking about timescales so vast that evolution, both biological and technological, has enormous scope to respond and adapt. As we continue forward in our model of the Sun's future, we reach a critical point about 5 billion years from now. By this time, the hydrogen in the Sun's core will be largely exhausted, replaced by an inert helium core that's slowly contracting under its own gravity. Unable to sustain fusion in its core, the Sun will begin fusing hydrogen in a shell around the helium core. This shell fusion is actually more efficient than core fusion, producing more energy, and this extra energy will cause the Sun's outer layers to expand dramatically. This is the beginning of the red giant phase, and it's a fascinating process from a physics perspective. As the outer layers expand, they cool, which is why the Sun will appear red rather than yellow-white. Red is the colour of cooler stars, though cooler is relative here. We're still talking about temperatures of thousands of degrees. The Sun's surface, currently about 500 degrees Celsius, will cool to perhaps 3,000 degrees, but its vastly increased size will mean its total energy output actually increases. During this red giant phase, the Sun will become increasingly unstable. That steady, reliable fusion that has characterized our star for billions of years will give way to a more chaotic process. The Sun will experience thermal pulses, periods where the fusion rate increases dramatically, causing the star to brighten and expand, followed by quieter periods. These pulses might last thousands or tens of thousands of years each, mere moments in stellar time, but each one will blow away some of the Sun's outer layers, enriching the surrounding space with elements forged over the Sun's lifetime. The Sun will lose perhaps half its mass during the red giant phase, blown away in an increasingly strong stellar wind. This mass loss has profound implications for the solar system. As the Sun loses mass, its gravitational grip weakens, and the planet's orbits expand. Mercury and Venus will almost certainly be engulfed by the expanding Sun, their material vaporized and mixed with the solar atmosphere. But Earth's fate is less certain. The expanding orbit might save it from direct engulfment, or tidal forces and atmospheric drag might cause it to spiral inward. The uncertainty in our models isn't a failure of science, but a reflection of the complex interplay of forces involved. What we do know is that even if Earth escapes direct engulfment, it will be completely transformed. The intense radiation from the bloated red giant Sun will strip away any remaining atmosphere, boil away any remaining water, and possibly even melt the surface rocks. Earth will become a barren, airless world, perhaps glowing dull red from its own heat, orbiting within or just outside the Sun's extended atmosphere. It's a far cry from the blue marble we know today, but remember, This is 5 billion years in the future. Earth will have had an incredible run by then, hosting life for perhaps 8 or 9 billion years total. As the red giant phase progresses, something remarkable will happen in the Sun's core. The temperature and pressure will eventually become high enough to ignite helium fusion, a process called the helium flash. In more massive stars, this happens gradually, but in stars like our Sun, it happens suddenly, over the course of just a few minutes. The entire helium core, which has been building up for billions of years, suddenly begins fusing into carbon and oxygen. The energy release is enormous, equivalent to billions of supernovae, but it all happens deep in the Sun's interior, absorbed by the overlying layers before it can escape. After the helium flash, the Sun will settle into a new equilibrium, fusing helium in its core and hydrogen in a shell around the core. This phase will last about 100 million years, a relatively brief period in the Sun's life. During this time, the Sun will shrink somewhat from its maximum red giant size, becoming what astronomers call a horizontal branch star. But this is just a temporary reprieve. Once the helium in the core is exhausted, the Sun will expand again, becoming an even larger red giant, what astronomers call an asymptotic giant branch star. This second red giant phase is even more dramatic than the first. The Sun will experience stronger thermal pulses, more mass loss, and greater instability. Its outer layers will become so loosely bound that they're barely held by gravity at all. Eventually, in a series of gentle exhalations rather than a violent explosion, the Sun will blow off its entire outer envelope, creating what astronomers call a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. They're called that because early astronomers thought they looked like planets through their telescopes. These planetary nebulae are some of the most beautiful objects in the universe. The expelled gas, glowing from the radiation of the exposed hot core, forms intricate structures: shells, rings, bipolar lobes, complex filaments. The Helix Nebula, the Ring Nebula, the Cat's Eye Nebula, these are all planetary nebulae created by stars similar to our Sun in their final acts of transformation. Each one is unique, shaped by magnetic fields, rotation, binary companions, and other factors we're still trying to understand. Our Sun's planetary nebula will expand outward at speeds of tens of kilometers per second, eventually reaching sizes of light years across. For about 10,000 years it will glow brilliantly, a cosmic work of art visible from distant star systems, and then, gradually, it will fade, the gas dispersing into the interstellar medium, enriched with carbon, nitrogen, oxygen, and other elements created during the Sun's life. These elements will eventually be incorporated into new stars, new planets, perhaps new life. And what of the Sun itself? After shedding its outer layers, all that will remain is the exposed core, a white dwarf about the size of Earth, but with about half the Sun's current mass. This white dwarf will be incredibly hot at first, perhaps 100,000 degrees Celsius at its surface, but it will have no source of new energy. It will simply cool gradually over trillions of years, its light fading from white to yellow to orange to red, and eventually, in a future so distant it's almost meaningless to contemplate, to black. But even as a white dwarf, the Sun won't be truly dead. It will still have gravity, still have magnetic fields, still interact with its environment. If any planets survive the red giant phase, they'll continue orbiting the white dwarf, though in much more distant orbits than today. The white dwarf might accrete matter from the interstellar medium, causing occasional flares. It might encounter other stars in its journey around the galaxy, perhaps being captured into a binary system, perhaps even merging with another white dwarf in a Type Ia supernova, billions or trillions of years in the future. The atoms that make up the white dwarf, primarily carbon and oxygen with traces of other elements, will essentially last forever. They'll remain bound in the white dwarf's intense gravity for trillions upon trillions of years, longer than the current age of the universe by factors of thousands or millions. In the far, far future, when the universe is cold and dark and all the stars have burned out, these white dwarfs will be among the last objects still shining, faint embers of a universe that was once bright with stars. As you contemplate these vast futures, these transformations that play out over billions and trillions of years, I want you to notice how your breathing has probably slowed, how your body has relaxed even further into wherever you're resting. There's something deeply calming about contemplating cosmic time, about recognizing that the universe operates on scales that make our human concerns seem both insignificant and precious. We are mayflies dancing in a cosmic summer afternoon, brief but beautiful, temporary but essential to the story being told. The sun's journey from main sequence star to red giant to white dwarf is not unique. It's the path that all stars of similar mass follow, a well-worn trail through stellar evolution. When we look at the night sky, we can see stars at every stage of this journey. Sirius, the brightest star in our night sky, is a main sequence star like our Sun but more massive and hotter. Arcturus and Aldebaran are red giants, showing us what our Sun will look like in 5 billion years. The companion to Sirius, Sirius B, is a white dwarf, showing us the Sun's ultimate fate. This universality, this commonality of stellar evolution, tells us something profound about our universe. The same physical laws that govern our Sun govern every star we can see. The fusion reactions happening in the Sun's core right now are the same reactions happening in stars in distant galaxies billions of light years away. The gravity that holds the Sun together is the same gravity that shapes galaxy clusters and the large-scale structure of the universe itself. We're all part of the same cosmic story, following the same physical laws, participating in the same grand evolution. And yet, within this universality, there's endless variety. No two stars are exactly alike. Small differences in mass, composition, rotation rate, magnetic field strength, the presence or absence of companion stars, all these factors influence how a star evolves, how long it lives, what kind of death it dies. Our Sun is unique in its particular combination of properties, and that uniqueness has allowed for the particular story of our solar system, our planet, our life. Scientists have discovered that stars slightly more massive than our Sun, say 1.5 times the Sun's mass, evolve much faster, living for only 3 or 4 billion years instead of 10 billion. If our Sun had been just a bit more massive, it would already be entering its red giant phase, and complex life might never have had time to evolve on Earth. Stars slightly less massive than our Sun, say 0.8 times the Sun's mass, can live for 15 or 20 billion years or even longer. If our Sun had been a bit less massive, it would still have trillions of years of stable burning ahead of it. This sensitivity to initial conditions, this way that small differences can lead to vastly different outcomes, is a recurring theme in astronomy and cosmology. It's what makes the universe so rich, so varied, so full of possibilities. Every star system is an experiment in planetary formation and evolution. Every planet is a potential stage for the emergence of complexity, perhaps even life. And while the vast majority of these experiments probably don't lead to anything as complex as what we see on Earth, the sheer number of stars and planets in the universe, hundreds of billions in our galaxy alone, suggests that we're probably not unique, probably not alone. As we continue to observe other star systems, we're finding planets in all sorts of configurations we never expected. Hot Jupiters orbiting close to their stars, super-Earths with no analogue in our solar system, planets orbiting binary stars, rogue planets drifting through interstellar space without any star at all. Each of these systems tells us something about planetary formation and evolution, about the range of possibilities, about our own system's place in the cosmic zoo. Some of these planets orbit red giant stars, giving us a preview of what our own solar system might look like in 5 billion years. Astronomers have found planets that apparently survived their star's red giant phase, now orbiting white dwarfs at distances that suggest their orbits expanded as their star lost mass. We've even found evidence of planets that didn't survive, their remains detectable as pollution in white dwarf atmospheres, heavy elements that shouldn't be there unless they were recently accreted from destroyed planets. These observations give us confidence in our models of stellar evolution and planetary system dynamics. They show us that the processes we've calculated and simulated actually happen in nature. They also show us that there's still much to learn, still mysteries to solve, still surprises waiting to be discovered. Every new observation adds another piece to the puzzle, another chapter to the story of how stars and planets evolve together over cosmic time. The James Webb Space Telescope, launched in 2021 and operational since 2022, has revolutionized our ability to observe stellar evolution in action. It can peer through the dust clouds where new stars are being born, watch the final gasps of dying stars, analyse the atmospheres of planets orbiting other stars. It's showing us stellar nurseries where the next generation of stars is forming from the ashes of previous generations, regions where the cycle of stellar life and death continues its eternal round. JWST has observed some of the oldest stars in the universe, formed just a few 100 million years after the Big Bang, when the universe was very different from today. These ancient stars were made almost entirely of hydrogen and helium, with virtually none of the heavier elements that exist today. They show us how stellar evolution has changed over cosmic time, how each generation of stars has enriched the universe with heavier elements, making possible the formation of rocky planets like Earth and the chemistry of life as we know it. We've also observed stars in their death throes, capturing images of planetary nebulae in unprecedented detail, watching as stars blow off their outer layers in beautiful, complex patterns. Each planetary nebula is a work of art, a unique expression of the physical processes that shaped it. Some are perfectly spherical, others are bipolar with lobes extending in opposite directions. Still others are irregular, chaotic, beautiful in their complexity. The Sun's eventual planetary nebula will be its final artistic statement, its last gift to the universe before settling into the long, quiet cooling of white dwarfhood. But let's return to that question of time, of the vast scales we've been discussing. How do we really comprehend billions of years? How do we grasp timescales that are millions of times longer than all of recorded human history? One way is through metaphor, through comparison, through scaling things down to sizes we can understand. So let me offer you another way to think about the Sun's life and Earth's place in it. Imagine the Sun's entire 10 billion year lifespan as a single year, from January 1st to December 31st. The Sun formed on January 1st, along with the rest of the solar system. Earth formed a few days later, let's say January 5th. Life appeared on Earth surprisingly early, perhaps around February 20th. But for months and months from February through October, life remained microscopic, single-celled, simple. The great oxidation event, when photosynthetic bacteria filled the atmosphere with oxygen, happened around June 15th. Complex cells with nuclei didn't evolve until early September. The Cambrian explosion, when complex multicellular life really took off, didn't happen until November 15th. Dinosaurs appeared on December 10th and went extinct on December 25th, just 6 days ago in our compressed timeline. The entire history of mammals fits into the last week of December. Humans, our species Homo sapiens, appeared at about 11:30 p.m. on December 31st, just half an hour before midnight. All of recorded human history, from the invention of writing to now, has happened in the last 30 seconds before midnight, and the Sun's transformation into a red giant. That doesn't begin until June of the following year, 6 months into the future. We're living in the Sun's middle age, in the stable, comfortable middle of its life story. There's no rush, no impending doom, just the slow, steady progression of stellar evolution playing out over timescales that dwarf human comprehension. This perspective can be deeply comforting when you really absorb it. All of our human dramas, all of our civilizations rising and falling, all of our wars and peace treaties, all of our art and science and philosophy, it's all happening in the blink of an eye from the Sun's perspective. And yet, that blink of an eye is our entire world, filled with meaning and beauty and complexity. We're like a single beautiful note in a cosmic symphony that's been playing for billions of years and will continue for billions more. As you lie there, perhaps feeling yourself drifting closer to sleep, I want you to feel yourself as part of this vast temporal landscape. Your life, brief as it may be on cosmic scales, is connected to everything that came before and everything that will come after. The atoms in your body have already existed for billions of years and will continue to exist for billions more. You're a temporary arrangement of eternal matter, a brief constellation of ancient atoms that have come together to create consciousness, to create awareness, to create the ability to contemplate your own place in the cosmic story. The sun that warmed you today is the same sun that warmed the dinosaurs, the same sun that will warm whatever beings exist on Earth 1,000,000 years from now. Its light connects us across vast spans of time, a constant in the ever-changing story of a life on Earth. When you feel sunlight on your face, you're feeling energy that was generated in the sun's core perhaps 1,000,000 years ago. that slowly made its way to the surface through countless interactions, and then travelled 93 million miles through space in just over 8 minutes to reach you. You're connected to the sun not just in space, but in time, part of a relationship that stretches across cosmic ages, and that relationship will continue long after you're gone, long after our species is gone, long after Earth itself is transformed beyond recognition. The sun will continue its journey through stellar evolution, and the atoms that make up your body will continue their journey through cosmic time. Perhaps some of them will be part of the sun's red giant envelope 5 billion years from now. Perhaps they'll be blown out into space in the sun's planetary nebula, drifting through the interstellar medium for millions of years before being incorporated into a new star, a new planetary system, perhaps even new life. This is the true meaning of immortality, not the continuation of individual consciousness, but the continuation of matter and energy through endless transformations. We are temporary patterns in an eternal flow, brief eddies in a cosmic stream that has been flowing since the Big Bang and will continue flowing until the universe itself ends, whatever that ending might look like. And in our brief moment of awareness, we get to appreciate the beauty of it all, the grandeur, the complexity, the deep peace of cosmic time. The sun's slow transformation from main sequence star to red giant to white dwarf is just one thread in this vast tapestry, but it's our thread, the one we're most intimately connected to. Understanding this transformation, appreciating the timescales involved, recognizing our place in the story, this can bring a profound sense of peace, a cosmic perspective that makes our daily worries seem manageable, our problems solvable, our lives meaningful despite their brevity. As we prepare to explore even deeper into the mechanisms of stellar evolution, into the specific physics that drives the sun's transformation, remember this feeling of temporal vastness, this sense of being part of something immeasurably larger and longer than yourself. Let it calm your mind, slow your breathing, relax your body. You're safe in this moment, in this brief island of stability in the flow of cosmic time. The sun will rise tomorrow, and for countless tomorrows to come. Earth will continue its faithful orbit, and you, made of star stuff powered by stellar fusion, connected to everything in the universe through the fundamental forces of nature, can rest peacefully in the knowledge that you're exactly where you're supposed to be when you're supposed to be there. Part of a story that's been unfolding for billions of years and will continue unfolding for billions more. Now, let's journey even deeper into the heart of our star, into the nuclear furnace where the magic happens, where matter transforms into energy in a process that's been powering the sun for billions of years and will continue for billions more. The sun's core is a place of extremes, temperatures of 15 million degrees Celsius, pressures 250 billion times greater than Earth's atmospheric pressure at sea level, densities 150 times that of water. It's a realm where matter behaves in ways that seem almost magical, where the normal rules of chemistry break down, where atoms are stripped of their electrons and nuclei can overcome their mutual repulsion to fuse together. The primary fusion reaction in the sun's core is called the proton-proton chain, and it's a marvel of quantum mechanics and nuclear physics. It starts with 2 protons, the nuclei of hydrogen atoms coming together. Now, protons are positively charged, and like charges repel, so normally these protons would never get close enough to fuse. But at the extreme temperatures in the sun's core, some protons are moving fast enough to get very close to each other, and when they do, quantum mechanics allows them to tunnel through the repulsive barrier, essentially teleporting through a wall they shouldn't be able to climb over. When 2 protons fuse, something remarkable happens. One of the protons transforms into a neutron, releasing a positron, the antimatter version of an electron, and a neutrino. This leaves us with deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. This first step is actually the slowest, the bottleneck in the whole process. On average, a proton in the sun's core will bounce around for billions of years before successfully fusing with another proton. This slowness is actually a good thing. If fusion happened faster, the sun would burn through its fuel much more quickly and wouldn't provide the billions of years of stability needed for life to evolve. Once deuterium is formed, things happen much faster. The deuterium quickly fuses with another proton to form helium-3, and then 2 helium-3 nuclei fuse to form helium-4. releasing 2 protons back into the mix. The net result is that 4 hydrogen nuclei have been converted into 1 helium nucleus, with a tiny bit of matter converted into energy, according to Einstein's famous equation, E is mc2. The amount of matter converted to energy in each reaction is minuscule, only about 0.7% of the original mass. But when you multiply that by the countless reactions happening every second in the Sun's core, you get the enormous energy output that lights up our solar system. Every second, the Sun converts about 4 million tons of matter into pure energy. That's the equivalent of billions of nuclear bombs going off every second, yet it's all happening in a controlled, steady manner that's been going on for billions of years. The energy released in these fusion reactions doesn't immediately leave the Sun. In fact, it begins an incredibly long journey from the core to the surface. The core is so dense that photons of light can only travel a tiny distance before being absorbed by an atom and then re-emitted in a random direction. This process, called radiative diffusion, means that energy moves through the Sun's interior like a drunk person trying to walk home, taking countless random steps, sometimes moving backward, slowly making progress toward the surface. In the radiative zone, which extends from the core to about 70% of the Sun's radius, it takes an average of 170,000 years for energy to make its way from the bottom to the top. Think about that for a moment. The sunlight warming your face today contains energy that was generated when humans were still in the Stone Age, before the invention of agriculture, before the rise of any civilization we know of. The Sun is so large, so dense, that it takes geological timescales just for energy to escape from its interior. Above the radiative zone is the convection zone, where the temperature has dropped enough that atoms can hold on to some of their electrons, making the material opaque to radiation. Here, energy transport switches from radiation to convection, with huge cells of hot gas rising to the surface, cooling and sinking back down, like water boiling in a pot. These convection cells are enormous, some as large as Texas, and they give the Sun's surface its granulated appearance, constantly churning and changing on timescales of minutes to hours. The surface of the Sun, what we call the photosphere, is where the gas finally becomes transparent enough for light to escape into space. This is what we see when we look at the Sun, though never directly, of course, as that would damage our eyes. The photosphere is only about 500 kilometers thick, incredibly thin compared to the Sun's radius of 696,000 kilometers, like the skin on an apple. Yet this thin layer is where all the sunlight that reaches Earth originates, where the energy that's been percolating up from the core for hundreds of thousands of years finally breaks free and streams across space. Above the photosphere is the chromosphere, a layer of hot gas that's usually invisible except during solar eclipses, when it appears as a reddish ring around the blocked Sun. And above that is the corona, the Sun's outer atmosphere, which extends millions of kilometers into space, and is, paradoxically, much hotter than the surface, reaching temperatures of millions of degrees. Scientists are still trying to fully understand why the corona is so hot, one of the enduring mysteries of solar physics. The solar wind, that stream of charged particles constantly flowing away from the Sun, originates in the corona. These particles, mainly protons and electrons, stream outward at speeds of hundreds of kilometers per second, carrying with them the Sun's magnetic field. When they reach Earth, they interact with our planet's magnetic field, creating the beautiful auroras, the northern and southern lights. They also pose a danger to astronauts and satellites, a reminder that our relationship with the Sun is complex, both life-giving and potentially hazardous. The Sun's magnetic field is generated by the movement of charged particles in its interior, a process called the solar dynamo. This magnetic field is incredibly complex and constantly changing, with field lines emerging from the surface, looping through the corona and diving back down. Sometimes these field lines get twisted and tangled, storing enormous amounts of energy that can be released suddenly, in solar flares and coronal mass ejections, explosive events that can send billions of tons of matter hurtling through space. The Sun's magnetic field goes through an 11-year cycle, flipping its polarity every cycle, so that the north and south magnetic poles switch places. During solar maximum, the peak of the cycle, the Sun is covered with sunspots, dark regions where strong magnetic fields suppress convection. During solar minimum, sunspots almost disappear, and the Sun appears relatively quiet. We're currently in solar cycle 25, which began in December 2019 and is expected to peak around 2025. These cycles within cycles, patterns within patterns, they all contribute to the sun's complex behaviour. Yet beneath all this activity, the fundamental process of fusion in the core continues steadily, slowly converting hydrogen to helium, slowly building up the ash that will eventually trigger the sun's transformation into a red giant. It's like a clock with many hands moving at different speeds, seconds, minutes, hours, days, years, all marking different aspects of time, but all driven by the same fundamental mechanism. Scientists study the sun's interior using a technique called helioseismology, analysing the way sound waves propagate through the sun. Just as seismologists use earthquake waves to study Earth's interior, helioseismologists use the sun's natural oscillations caused by convection near the surface to probe its hidden depths. The sun rings like a bell, with millions of different modes of oscillation, each telling us something about the temperature, density, composition, and motion of different parts of the solar interior. These observations have confirmed our theoretical models of stellar structure to remarkable precision. We can measure the depth of the convection zone, the rotation rate at different depths and latitudes, the speed of sound throughout the interior, even subtle changes in the core as hydrogen is converted to helium. It's like having ultrasound images of the sun's interior, allowing us to see what's happening in regions that will never be directly observable. One of the most remarkable discoveries from helioseismology is that the sun's core rotates faster than its surface, completing a rotation in about 25 days compared to 35 days at the poles. This differential rotation is thought to play a key role in generating the sun's magnetic field. We've also discovered that the rotation rate changes over time, speeding up and slowing down in complex patterns that we're still trying to understand. Neutrino observations provide another window into the sun's core. Neutrinos are ghostly particles produced in fusion reactions that barely interact with matter, allowing them to escape from the sun's core immediately, reaching Earth in just 8 minutes. By detecting these neutrinos, we can directly observe fusion happening in the sun's core right now, not 170,000 years ago, like with light. Neutrino, observatories deep underground have confirmed that fusion is happening at the predicted rate, another triumph for our understanding of stellar physics. The study of the sun has also revealed the incredible fine-tuning required for stars to burn steadily for billions of years. If the strong nuclear force were just 2% stronger, protons would fuse too easily, and stars would burn out quickly. If it were 2% weaker, protons couldn't fuse at all, and there would be no stars. If gravity was slightly different, stars would either collapse immediately or never form. The universe seems to be balanced on a knife's edge, with physical constants that are just right for the formation of long-lived stars like our sun. This fine-tuning extends to the specific reactions that power the sun. The proton-proton chain involves several delicate steps, each with its own probability and rate. The fact that these rates work out to give us a star that burns steadily for 10 billion years seems almost miraculous. Some scientists see this as evidence of a multiverse, where countless universes exist with different physical constants, and we naturally find ourselves in one where stars can exist and life can evolve. Others see it as a deep puzzle about the nature of physical law, why the constants are what they are. As you contemplate these mysteries, feeling perhaps the gentle pull of sleep beginning to take hold, consider how remarkable it is that we can understand the sun at all. Here we are, tiny beings on a small planet, and yet we've figured out how to peer into the heart of a star, to understand processes happening at temperatures and pressures we can never directly experience, to predict with remarkable accuracy what will happen billions of years in the future. It's a testament to the power of human curiosity and intelligence, but also to the comprehensibility of the universe, the fact that it follows mathematical laws that we can discover and understand. The sun's story is written in the language of physics, in equations that describe how matter and energy behave under extreme conditions. These same equations tell us that eventually, inevitably, the sun will exhaust its hydrogen fuel and begin its transformation into a red giant. But they also tell us that this transformation is billions of years away, that we have an almost unimaginable amount of time before we need to worry about it. The equations give us both knowledge and peace, understanding and perspective. As we move forward to explore what this transformation will mean for Earth, for the solar system, for any life that might still exist billions of years from now, carry with you this sense of deep time, this appreciation for the slow majesty of stellar evolution. The sun's journey from birth to death is not a tragedy but a natural process, as natural as the cycle of seasons or the rhythm of waves on a shore. It's the way stars are meant to evolve, the path written into the laws of physics from the moment of the Big Bang. And we, brief as we are, get to be part of this story. We get to bask in the sun's light during its stable middle age. We get to understand our star in ways that no other species on Earth ever has. We get to appreciate the cosmic context of our existence, to see ourselves as part of a vast, beautiful, ongoing process of cosmic evolution. That's a privilege, a gift, a source of wonder that can fill us with awe and peace in equal measure. The sun continues its steady burn as you drift towards sleep, fusing hydrogen into helium at a rate that's been constant for billions of years. Tomorrow it will rise as it has every day of your life, every day of human history, every day for billions of years before humans existed. There's comfort in that continuity, peace in that reliability. The sun is patient. The universe is patient. And in that patience, that vast cosmic patience, we can find our own peace, our own rest, our own place in the grand story of stellar evolution. Now we arrive at the heart of the mystery, the moment when our sun will transform so completely that Earth itself may vanish into its glowing embrace, though perhaps not in the way you might imagine. As you settle even deeper into rest, perhaps feeling that soft boundary between waking and sleeping beginning to blur, I want to paint for you a picture of transformation, so gradual, so patient, that if you could somehow watch it unfold, it would be like watching a cosmic flower bloom over millions of years, each petal of light expanding outward with infinite slowness, infinite grace. The word swallow carries such dramatic implications, doesn't it? It suggests something sudden, violent, consumptive. But in the language of stars, in the vocabulary of cosmic evolution, swallowing is more like breathing, more like embracing, more like the slow merger of two things that were always meant to become one. When we say the sun will swallow Earth, we're really talking about a reunion of matter that has been separated for billions of years, a coming together that closes a circle that began when both sun and Earth formed from the same swirling cloud of gas and dust. Let me take you forward in time now, not the mere thousands or millions of years we can almost imagine, but 5 billion years into the future, to that pivotal moment when the sun begins its transformation from the star we know into something altogether different, altogether magnificent in its own way. By this time, the hydrogen in the sun's core will be largely exhausted, replaced by an inert ball of helium that sits at the centre, like a pearl that cannot yet shine. The fusion that has powered our star for 10 billion years will have moved outward, forming a shell around this helium core where hydrogen still burns, but burns differently now, more intensely, more desperately perhaps, if stars could be said to feel desperation. This shell burning is actually more efficient than the core burning that's happening right now. It produces more energy per unit of fuel, and all that extra energy has to go somewhere. Unable to escape quickly enough through the sun's dense interior, this energy pushes outward on the stellar envelope, causing it to expand, to swell, to grow beyond anything we would recognize as our familiar sun. Over the course of just a few million years, a blink of an eye in cosmic time, but still far longer than our species has existed, the sun will grow from its current size to perhaps 200 times its present radius. Imagine standing on Earth during this transformation, if Earth still existed in any recognizable form, if there were still beings capable of standing and observing. The sun would no longer be a disk in the sky, but would fill a huge portion of the heavens, a vast red orb that dominates the view, too large to take in with a single glance. The familiar yellow-white light would be replaced by a deep red glow, like permanent sunset, like the whole sky is ember and flame. But this flame is not hot in the way we think of flame. The sun's surface temperature will actually decrease as it expands, dropping from about 5,500 degrees Celsius to perhaps 3,000 degrees. It's the sheer size, the enormous surface area, that will make the red giant sun actually more luminous than our current sun, pouring out perhaps 2,000 times as much total energy. But here's where our story takes an interesting turn, where the not how you think part of our title becomes crucial. As the sun expands, it will also be losing mass at an unprecedented rate. The stellar wind, that stream of particles that even now flows constantly from our star, will become a gale, a hurricane of subatomic particles streaming into space. The sun might lose half its total mass during the red giant phase, blown away into the cosmos like seeds from a dandelion, like sand from a dune, like memories fading into time. This mass loss has profound implications for the planets, especially for Earth. You see, gravity depends on mass, and as the sun loses mass, its gravitational grip on the planets weakens. As that grip weakens, the planets respond by moving outward, their orbits expanding like ripples on a pond when the stone that created them begins to dissolve. Earth's orbit, currently at 150 million kilometers from the sun, might expand to 180 million kilometers, maybe even 200 million kilometers, as the sun sheds its outer layers. This orbital expansion might save Earth from direct engulfment. It's a cosmic race between the sun's expanding surface and Earth's retreating orbit, and scientists have run countless simulations trying to determine the outcome. Some models suggest Earth will narrowly escape, orbiting just outside the sun's bloated photosphere. Others, taking into account tidal forces and the drag of the sun's thin outer atmosphere, suggest Earth will spiral inward and eventually be vaporized. The uncertainty isn't a failure of science, but a reflection of the incredible complexity of the processes involved, the delicate interplay of forces that will determine Earth's ultimate fate. But let's think more carefully about what it means for Earth to be swallowed by the sun. If Earth does end up inside the sun's outer envelope during the red giant phase, it won't encounter anything like the dense hot plasma we associate with the sun today. The sun's outer layers during the red giant phase will be incredibly tenuous, less dense than what we would consider a good laboratory vacuum here on Earth. It would be like flying through an extremely hot, extremely thin fog, a luminous mist that gradually thickens as you descend deeper. Earth wouldn't suddenly vaporize or explode. Instead, it would experience a gradual heating as it orbited within this thin stellar atmosphere. The friction of passing through even this tenuous gas would cause drag on Earth's orbit, making it spiral slowly inward over thousands or millions of years. As it spiraled deeper, the temperature and density would increase, and Earth's surface would begin to melt, then vaporize. Its atmosphere long since stripped away, its oceans boiled off eons ago. Eventually the solid Earth itself would begin to ablate, to wear away like a meteorite entering an atmosphere, its matter mixing with the solar plasma, becoming part of the star that gave it life so long ago. There's something deeply poetic about this image, isn't there? Earth, after billions of years of faithful orbiting, finally returning to its source, its atoms mixing with solar material, becoming part of the star itself. Those atoms, the iron that once flowed in our blood, the calcium that once formed our bones, the carbon that once made up our DNA, they would become part of the sun's substance, perhaps eventually blown out into space when the sun sheds its outer layers, perhaps becoming part of new stars, new planets, new life in some unimaginable future. But let's not get ahead of ourselves. Let's stay with this moment of transformation, this period when the sun is a red giant and Earth's fate hangs in the balance. During this phase, the sun will be unstable in ways it never was during its main sequence lifetime. It will experience thermal pulses, periods where the rate of helium fusion in the core suddenly increases, causing the star to brighten and expand, followed by periods of relative calm. These pulses might last thousands of years each, and each one will blow away more of the sun's mass, enriching the space around it with carbon, nitrogen, oxygen, and other elements forged over the star's lifetime. If Earth survives to orbit the red giant sun, it will be a very different world from the one we know. The intense radiation will have long since stripped away any atmosphere, boiled away any water, probably melted and resolidified the surface rocks multiple times. Earth might glow with its own heat, a ball of molten rock orbiting within or just outside the sun's extended atmosphere. Any mountains, any geological features we might recognize will have been erased. The continents, the ocean basins, all the familiar geography of our world will be gone, replaced by a smooth sphere of cooling lava, or perhaps by something we can't even imagine. And yet, even in this transformed state, Earth would still be Earth in some fundamental sense. The same atoms that make it up now would still be there, just rearranged, reformed, transformed by heat and radiation and time. The The core of iron and nickel that gives Earth its magnetic field might still exist, still spinning, though probably more slowly after billions of years of tidal interactions with the Sun. The planet's basic structure, its differentiation into core, mantle, and crust, might persist even through the extreme heating of the red giant phase. Scientists have actually observed planets orbiting red giant stars, giving us real-world examples of what Earth's situation might be like. Some of these planets orbit very close to their bloated stars, skimming just above the stellar surface, somehow surviving in that extreme environment. Others orbit at distances that suggest they migrated outward as their star expanded and lost mass. Each system tells us something about the possible fates of planets, around evolving stars, about the range of outcomes, about the resilience or fragility of worlds in the face of stellar transformation. One particularly fascinating discovery is planets orbiting white dwarfs, the remnants of stars that have already gone through the red giant phase and shed their outer layers. These planets must have survived their star's transformation, adjusting their orbits as the star lost mass, enduring the intense radiation of the red giant phase, and emerging on the other side to continue their cosmic journey around a stellar corpse. If such survival is possible, perhaps Earth too might make it through the Sun's red giant phase, transformed beyond recognition but still orbiting, still continuing its billion-year dance with our star. The key factor in Earth's survival or destruction will be the delicate balance between orbital expansion, due to the Sun's mass loss, and orbital decay due to tidal forces and atmospheric drag. Tidal forces arise because the side of Earth facing the Sun experiences slightly stronger gravity than the far side, creating a stretching force that can transfer angular momentum from Earth's orbit to the Sun's rotation. This transfer causes Earth's orbit to slowly decay, spiraling inward over millions of years. The effect is tiny now, completely negligible, but it will become more pronounced as the Sun expands and Earth orbits within or near its outer atmosphere. The drag force is even more uncertain because it depends on the exact density of the Sun's outer atmosphere at Earth's orbital distance, which depends on details of the Sun's structure and mass loss rate that we can't predict with perfect accuracy. It's like trying to predict exactly where a leaf will land when it falls from a tree. There are too many variables, too many small effects that can add up to large differences in outcome. We can calculate probabilities, we can run simulations, but we can't say with certainty whether Earth will be swallowed or will survive. And perhaps that uncertainty is appropriate, even beautiful in its own way. It means Earth's fate remains an open question, a mystery that won't be resolved for billions of years. It leaves room for possibility, for hope if you're inclined to hope for Earth's survival, or for acceptance if you prefer to imagine Earth returning to its stellar origin. The universe doesn't always give us definitive answers. Sometimes it leaves us with questions, with wonders, with mysteries that can occupy our minds as we drift off to sleep.